According to General Dwight D. Eisenhower and many other historians, the Bailey Bridge was one of the 3 most vital innovations for the Allied victory in World War II. This rugged, easy-to-assemble bridge still does wonders even in the modern world. In fact, these structures of the Bailey Bridge are not mere railings. They are the side panels that give incredible strength to the Bailey Bridge. For example, if you just arrange a few metal pieces like this, they don't have much strength. Now, let's arrange the same metal pieces in the form of a truss. This provides incredible strength. Keep 2 such trusses and connect them using these bars. This is the basic Bailey Bridge. You can easily see how this truss bridge will be able to carry a huge amount of load. The load is initially carried by the road deck, which is ultimately transferred to the strong trusses. The theory is easy, but how can the Army assemble such a huge bridge without crossing the river? Erection of this bridge is a brilliant example of balancing weights. Welcome to the genius engineering of Sir Donald Bailey. The first step in the Bailey Bridge assembly is the installation of these rollers. One roller is quite special among them, the rocker roller. These rollers are tiltable. This simple-looking side panel is the genius part of the Bailey Bridge. This structure is rugged, yet lightweight. 5 to 6 people can easily lift it. Now, place 2 side panels above the roller. Next, they insert a heavy I-channel called a transom in between these side panels. This side support bar makes the transom's connection strong. 1 unit of the Bailey Bridge is ready. Next, they introduce the next set of side panels. Look at the male-female portions of the side panels. They fit perfectly and are locked with these pins. These sway braces are attached before the transom. Sway braces make the bridge shape rugged. The next side panel connection is crucial. This is connected after adding an extender, and eventually the new side panel connects with the previous one at an angle. We will soon see why this angle is needed. Just add 1 more pair of side panels. The weight is now equal in both sections. What will happen now if a few soldiers push the structure forward? Yes, the bridge will easily get tilted and it will rest symmetrically between 2 rollers. Let's connect 1 more side panel. Weight is more on the left side now. The bridge gets tilted further and eventually it rests on the other side, the left side. Now comes the most crucial part of the video. The weight management of the Bailey Bridge. This is the main roller of the Bailey Bridge. If the weight balance goes wrong, the Bailey Bridge will topple as shown. Please note where the pivot point is during this topple. It's at the main roller. So, for a successful Bailey Bridge launching, the torque on the left side should be greater than that on the right side. Otherwise, the launching will end in a tragedy. But in the last stage of the erection, the right side torque should become higher. If you've forgotten what torque is, you may recollect it from this childhood example. Sometimes torque will be higher on the low weight side. Anyway, let's see how this clever operation is done. Soldiers can now push and move this portion of the bridge. The torque on the right side is obviously smaller than that of the left side. This structure is stable. Now the assembly work of the main portion of the bridge starts. Soldiers want to drive even heavy vehicles on this bridge. To support such heavy load, the trusses of the Bailey Bridge should be super strong. Let's use a triple truss and double story panel arrangement for the main portion of the bridge. Details of their connections are shown here. It should be noted that there exists single and double truss panel arrangements as well, with different story options. The weight of this single truss unit is around 1,300 kilograms, while the weight of the triple truss unit is around 4,200 kilograms. Assume the soldiers have pushed the bridge forward by exactly the distance of 1 unit of the side panel. The left side portion of the bridge is marked with white, and the right side portion with red color. This marking is important for torque calculation. The bridge looks a little dangerous now. Anyway, let's check the torque on both sides. The torque on the left side is much higher than the right side. The bridge is stable. Let's assemble more pieces of the bridge and push it forward again. This position of the bridge is also stable. This time, the soldiers have to assemble 2 more sections before pushing the bridge further. The bridge is hanging too much in the air, and it seems like it's going to topple into the river. Let's do a torque analysis to clear our doubts. Surprisingly, this position is also stable. Sir Donald Bailey's precise mathematics saved the Bailey Bridge. Let's add 1 more section and push the bridge forward. The torque on the left and right sides are almost equal now. Still, it's higher on the left side. 2 more pieces and a push of 1 unit length. The torque is still higher on the left side, and the bridge is stable yet again. The reason why we made the front portion bent upward might be clear to you now. Currently, the bridge is supported only at one end. Due to its self-weight, the structure deflects a lot. If this upward bend were not there, the free end of the bridge would have gone below the level of the other riverbank. Donald Bailey is a genius, right? Anyway, what you have to do now is just add 1 more section and push the bridge forward by exactly 1 unit length. Here, obviously, the torque produced by the left side remains the same, but the torque at the right side has increased. For the first time, the right side torque has exceeded the left side torque. This will cause the free end of the bridge to automatically fall to the ground. This is a big moment for the soldiers. The big phase of the project is over. Let's watch this crucial moment one more time in slow motion. Sir Donald Bailey played with weight balance calculations so cleverly. Now, a few soldiers can cross the bridge and lift the other end using a hydraulic jack. In this end also, they install a roller bearing. Now, the soldiers go for a long push until the entire river is covered with the triple truss Bailey Bridge. It's time to remove the single truss supporting portion of the bridge. The bridge is almost ready. What you have to do is add some end support, and after that, a bearing at the end of the bridge. You may remove the rollers now. A robust and durable bridge is ready for military use. When the bridge carries a heavy load, it deflects a little bit as shown. These bearings make sure that this slight deflection is allowed. If these bearings were not present, the bridge would have undergone too much internal stress.
Here is one interesting experiment to test strength of a Bailey bridge. Let's first start with a normal bridge. This simple bridge is not even able to carry a weight of 25 kg. It's deflating too much. Here in the new case at the end of the road deck, I have attached Bailey bridge trusses. That too, trusses made up of simple popsicle sticks. Look at the way the new bridge is carrying the weight. The bridge is not at all getting deflated for the same 25 kg. That's the magic of Bailey bridges.
Nowadays, Bailey bridges are built mostly for civilian uses. When natural calamities strike, this is often the only way to establish connection with the other part of the river. Even though they're built for temporary purposes, they eventually become permanent bridges. All these discussions will naturally lead to a question: which is the longest Bailey Bridge in the world? This record goes to the Hobart Bailey Bridge, which crossed the Derwent River at Dowsing's Point. The bridge had an impressive 788 meters in length and had 2 lanes. The Hobart Bailey Bridge was built as a temporary solution when bulk carrier SS Lake Illawarra collided with the Tasman Bridge in Hobart, causing 2 piers and 127 meters of the bridge deck to collapse. The new Bailey Bridge served as the sole road link between the eastern and western shores of Hobart for nearly 2 years until the Tasman Bridge was rebuilt and reopened on October 8, 1977. Of course, such a lengthy bridge needs support from the piers to carry the weight of the heavy vehicles. To understand the genius engineering of this bridge, we used these simple popsicle sticks and built a Bailey Bridge.
This bridge can carry even my weight. but just cut one of its railings. The bridge is deflating too much and finally collapsing.
Some original World War II Bailey bridges are still in regular use today, a testament to their robust design and durability. One such prototype bridge in Dorset, Ukraine, remains a functioning bridge.
Sir Donald Bailey is a true inspiration for all the civil engineers. If you like to see this channel to grow and thrive, please check out my Patreon page and try to support us. Take care, bye bye.